Hello my dear students, welcome back to Fluid Mechanics lecture series. I am your SumamMiss.
My channel name is also SumamMiss. You can watch my videos on my channel. Today we are continuing the discussion on the application of Bernoulli's equation for the measurement of discharge. We have learned previously about different flow measuring devices like venturimeter, orifice space, etc. So these flowmeters are developed based on the principle of continuity equation and Bernoulli's equation. So these flowmeters are also called differential flowmeters because for the computation of discharge, the only measurement we have to conduct in the field is the measurement of differential pressure head. The device which I am going to introduce today is Pitot tube. Pitot tube is used to measure the velocity of the stream. It is a simple L-shaped tube facing into the oncoming flow. Figure shows a glass tube bent at right angles and open at both ends. The tube is inserted into the flow with horizontal open end facing the flow. The liquid enters and the liquid level in the vertical open end rises up to the height h. So when this Pitot tube is used in open channels, h can be determined directly and can be utilized for the computation of velocity. Pitot tube can also be used to find out the velocity at any point in the pipes as well as in open channels. Figure shows a pipe which is running full. Now the Pitot tube is inserted into this pipe. So the liquid enters and the liquid level in the vertical open end rises. Now just compare this water level with respect to that of a piezometer which is inserted in this pipe at some other location. So you can see that the level of liquid in the Pitot tube is higher than that of piezometer. So piezometer is an instrument which is used to measure the static pressure. What may be the reason for the rise in liquid level in this Pitot tube? So piezometer represents the static pressure head H0, whereas the water level in the Pitot tube is indicated by H0 plus H. So H is the difference of water level between this Pitot tube and the piezometer. So within this pipe, the fluid is moving with flow velocity v. When it approaches and it touches the tip of this Pitot tube, the velocity of the fluid particle that is equal to 0. So the point at which the flow velocity that is equal to 0, that is called stagnation point, and the pressure correspond to the stagnation point is called stagnation pressure. At this point, the velocity head that is converted into pressure head. So that is designated by this pressure head H. So H0 plus H, which represents the total pressure head at this point A. So H0 that is the static head, whereas H0 plus H represents static head and the dynamic head. So dynamic head occurs because of the conversion of the velocity head to the pressure head. Now, how will you find out this flow velocity? For which we have to apply the Bernoulli's equation. So consider a point 1 which is in line with this point A. Now apply this Bernoulli's equation at this point 1 and A. So at this point 1, the total energy that is equal to P1 by rho g plus V square by 2g, that is equal to Pa by rho g plus Va square by 2g. So at this point A, flow velocity that is equal to 0. Now P1 by rho g that is equal to H0 plus V square by 2g, that is equal to Pa by rho g is H0 plus H plus Va square by 2g. So this Va square by 2g that is equal to 0. So if you are simplifying this expression, we'll get V square by 2g equal to H or V equal to root of 2gh. Since we haven't account any losses between the point 1 and A, the velocity we calculated is a theoretical velocity, that is root of 2gh. So actual velocity can be represented as Cp into root of 2gh, where Cp that is the coefficient of Pitot tube and its value varies between 0.98 to 1. When Pitot tube is used in open channels, H can be determined directly because in open channels every point is subjected to atmospheric pressure, so H can be determined directly. But when Pitot tube is to be used in pipes, The difference between the static pressure and the impact pressure at the hole must be determined with a differential pressure gauge using static pressure tapping in the pipe wall. Or we can connect one limb of this U-tube manometer to the vertical open end of this Pitot tube, and other end of this U-tube manometer we can connect to the point where we have to measure the static pressure. Because of the pressure difference, we can see a deflection in the manometric liquid. So we have to convert this deflection into pressure head. So that can be done by writing the pressure balance equation. How to write the pressure balance equation? We have to apply Pascal's law and sign concept. So we have to match the pressure at this level, that is Cc dash. So we can write down the pressure balance equation and equate that at the level Cc dash. So Pa by rho g, that is the pressure up to this, into x into s. S means specific gravity of this flowing liquid, that is equal to Pb by rho g, that is the pressure up to this level, plus x into Sm, where Sm is the specific gravity of this manometric liquid. So if we are simplifying, then the differential pressure head H equal to x into Sm by s minus 1, and velocity, that is equal to root of 2gh, or discharge equal to area into velocity. The tube recording the static pressure and the stagnation pressure are frequently combined into one instrument, that is called Pitot static tube. So here static tube surround the Pitot tube. So the inner tube which is used to measure the impact pressure, and this is a stagnation point, whereas the annular tube with holes on the surface which is used to measure the static pressure. And you can see a pressure transducer here. The pressure transducer which is connected here can be used to determine the difference in static pressure and the impact pressure. So the Pitot tube can also be used to compute the discharge by measuring the velocity of the flowing fluid. So here also the only measurement you have to do in the field is the measurement of the differential pressure head. The solution of the conceptual field problems are discussing in the next section. So in this figure, you can see that a pipeline which carries oil of specific gravity 0.877. So diameter of this pipe changes from 220 mm to 600 mm. So there are two sections A and B. So section A, that is 3 meters lower than the section B, and pressure at the section A and B are given. So we have to determine the flow direction and the head loss. So the discharge through the pipe, that is also given as 0.17 meter cube per second. So for the solution of this problem, we have to refer the continuity equation and the Bernoulli's equation. So first of all, we have to copy down all the data and we have to convert that into proper units. Since continuity equation is valid here, the discharge at the section A equal to discharge at the section B. Specific gravity of this oil is given, so we have to find out the specific weight of oil as multiplied the specific gravity S by specific weight of the water. So specific weight of water equal to rho g. Diameter at the section A and B are given, so we can calculate the area, and correspondingly we can calculate the velocity. So velocity at the section A equal to 4.4721 meter per second, and velocity at the section B is calculated as 0.6013 meter per second. So in order to find out the direction of the flow, we have to calculate the total energy at the section A and total energy at the section B. So always the flow is taking place from high energy to low energy. So let us apply the Bernoulli's equation at the section A and the section B. So at the section A, it is Pa by rho gs plus Va square by 2g plus Za, that is equal to Pb by rho gs plus Vb square by 2g plus Zb plus HL. That is HL equal to the total energy at the section A minus total energy at the section B. So total energy at the section A is indicated by HA, that is equal to Pa by rho gs plus Va square by 2g plus Za. Since this point as datum, Za equal to 0 and Pa that is available with us, VA, that is calculated as 4.4721 meter per second. So you can substitute and calculate the total energy at the section A, that is equal to 12.6427 meter. Similarly, we can calculate the total energy at the section B as PB by rho GS plus VB square by 2G plus ZB. So PB is given, that is 70 into 1000 Pascal. Then VB is, that is calculated. So VB square by 2G we can calculate. And ZB, that is the point B is 3 meter higher with respect to the point A. So ZB equal to 3. So total energy HB is calculated as 11.15477 meter. So we can see that the total energy at the section A is higher than the total energy at the section B. So always the flow is taking place from high energy to low energy. So the flow direction is from A to B. So the next part of the problem is the calculation of the head loss, that is equal to total energy at the section A minus total energy at the section B. So that you can calculate it as 1.4879 meter of oil. So this can be converted into Pascal by multiplying with rho GS, that is equal to 12.801 kilopascal. So this is one of the typical problem you can expect in the examination. So all of you can go through the problem and solve by your own and verify the answer. The next problem is also the direct application of Bernoulli's equation. So in this problem, a vertical conical draft tube of a turbine 2 meter long and kept vertical with a smaller diameter and facing up. So what is a draft tube? It is a part of this hydropower plant. It is attached directly to the turbine casing. So after passing through the turbine, the high velocity water is allowed to flow out through the draft tube. So the purpose of the draft tube is to reduce the velocity of the flowing water. So the measured pressure head at the smaller end is 2.5. That is P1 is given as 2.5. And the loss of head that is given as 0.35 into V1 minus V2 square by 2G, where V1 is the velocity at the upper end that is given and V2 is the velocity at the lower end that is also given. So we have to determine the pressure head at the lower end. So P2 is to be determined. So what we have to do is we have to apply the Bernoulli's equation at the section 1 and 2. P1 by rho g is available directly as 2.5 meter. V1 that is 4.5 meter per second. Z1 that is equal to 2. Similarly, P2 by rho g to be determined. V2 is available and Z2 that is equal to 0 because this is the datum level. And HL is given as 0.35 into V1 minus V2 the whole square by 2G. Okay, so you can substitute the values. So simplify this expression. So you will get P2 by rho g as 5.257 meter of water. So the pressure head directly available at this lower end that is equal to 5.257 meter of water. So please thorough with the conversion of the unit. This is one of the field problem. So in this problem, a fire engine is used to discharge water to the rooftop. So this is the tank of this fire engine. So it is partially filled with water. So we have to find out the pressure to be maintained here so that we can discharge 1200 lpm of water on the roof of this building, which is at a height of 2.5 meter above the water level in the tank. So the hose which is connected from this tank to this rooftop has the diameter 60 mm and the friction loss is given as 0.4 meter of water. So we have to get the value of the air pressure above the water surface in the tank. So here also we have to apply the content equation along with the Bernoulli's equation. First of all, we have to copy down all data and we have to convert that into proper unit. So discharge is converted from LPM to meter cube per second. Diameter of the hose is given in mm, so that is to be converted into meter. Z2 that is given as 2.5 meter, that is roof of the building is 2.5 meter above the water level in the tank. So Z2 is given. Now content equation is valid here, so we can calculate the flow velocity within the hose. So V2 equal to Q by A. Q is given to us. Area that is also available. So V2 can be calculated. Consider this level as the datum. So the water level within the tank is taken as section 1 and the rooftop that is taken as section 2. So apply this Bernoulli's equation at this water level and at the rooftop. So the total energy available at this section, that is equal to P1 by rho g plus V1 square by 2g plus Z1, that is equal to P2 by rho g plus V2 square by 2g plus Z2 plus HL. So at this water surface, flow velocity V1, that is equal to 0, and this is the datum level, so Z1, that is also 0. Then from this tank, water is discharged into the rooftop. So discharge velocity, that is V2, that is we calculated, and since it is discharging on the rooftop, P2 by rho g, that is atmospheric pressure, so that we can consider as 0, and HL, that is given as 0.4 meter of water, and Z2, that is also given as 2.5 meter. If we are substituting all these values, P1 by rho g, that is the pressure head available within this tank, and V1 square by 2g, that is equal to 0 because the flow velocity here equal to 0, and Z1, that is equal to 0. Then P2 by rho g, that is the pressure head available at this rooftop, that is also 0, plus V2 square by 2g plus Z2 plus loss. So P1 by rho g, you can calculate it as 5.45 meter of water, or that is equal to 53.467 kilopascal. So this problem also you can solve by your own and verify the answer. So the next problem is the computation of discharge using venturimeter. So venturimeter is connected to an inclined pipeline which is inclined an angle 30 degree. So this venturimeter throat diameter is given as 200 mm and this convergent length is given as 600 mm and pipe diameter, that is also given as 500 mm. It carries an oil of specific gravity 0.8. So this pipeline is laid at a slope of 30 degree with horizontal, and the flow is taking place from 1 to 2, that is in the upward direction. So the U2 manometer, which is connected at the point 1 and 2 to determine the differential pressure head, shows a deflection of 50 mm. So CD, that is given to us. So the first part of this problem is determination of the discharge. So we have copied down all these data and converted that into relevant unit. Diameter at the throat is given, so we can calculate the area A2 here. Similarly, the diameter of the pipe is available, so we can calculate A1 also. So in order to use this equation, the next part is we have to calculate the differential pressure head based on this deflection. So differential pressure head H equal to x into Sm by S minus 1, where x is the deflection, that is converted into meter, and Sm is the specific gravity of this manometric liquid, and S is the specific gravity of this flowing liquid. So in this problem, the specific gravity of the manometric liquid is not given. Normally we are using mercury as manometric liquid. Specific gravity of the mercury is equal to 13.6. So differential pressure head is calculated as 0.8 meter of oil. So for a venturimeter, the discharge equation is CD into A1 A2 into root of 2GH divided by root of A1 square minus A2 square, where A2 is the area at the throat, A1, that is the area at the convergent section. So diameter of the convergent section is as same as that of this pipe. So A1 is calculated, H also calculated. So Q is obtained as 0.1261 meter cube per second. In next part of the problem, this U2 manometers is replaced by pressure gauge. So one pressure gauge we have to keep at the entrance, and other pressure gauge we have to keep at the throat. So the pressure gauge at the entrance shows a reading of 140 kilopascal. So we have to determine the reading in the pressure gauge that is kept at the point 2. So what is H? H is the differential pressure head between the point 1 and 2, or it is the difference of piezometric head between the 2 points 1 and 2. So the piezometric head at the section 1 equal to P1 by rho gs plus Z1, and piezometric head at the section 2, that is equal to P2 by rho gs plus Z2. So we can consider this point as datum. So set 1 that is equal to 0. The section 2 is at a higher level with respect to the section 1. But the length of this convergent cone is given to us. So that is given as 600 mm or it is equal to 0.6 meter. And the inclination is also given, that is 30 degree. So set 2 that is equal to LC sin theta. If you are rewriting this expression, P1 by rho gs minus P2 by rho gs plus Z1 minus Z2 that is equal to H that we have calculated already. So P1 is available with us. So if you are substituting, then P1 by rho gs minus P2 by rho gs minus LC sin 30 that is equal to the pressure head. So P2 by rho gs that is equal to 16.73894 meter of oil, or it is equal to P2 into rho gs that is equal to 131.367 kilopascal. Pressure gauge which is connected at the section 2 shows a reading of 131.367 kilopascal. So all of you please go through the problem and solve by your own and verify all the answers. So without solving the problem, one cannot familiarize the basic concepts. So in this class, we started with the discussion on Pitot tube, followed with the methodology used for the solution of conceptual problems. Now the session comes to an end. For the time being, it is enough. Thank you.